Ladies and gentlemen, welcome to lesson number 2. And I think it is the last lesson for content teaching, Doppler's effect. Remember that I believe that teaching and answering question papers is not the same thing. When I teach, I start by teaching content on a general note. Then after we can do question paper. So this is the last lesson for teaching the content of Doppler's effect. Don't forget, if you have not subscribed to this channel, make sure that you subscribe. Press the subscribe button, press the notification button. Also, tell someone about this channel, how it is assisting you. When I go to different gatherings and I meet learners from different places, they always tell me that the lessons, they are assisting them. So I also advise that tell someone about us so that we can grow. Ladies and gentlemen, you are welcome. Today we are going to focus more on calculations, but we will also try to have a small recap with some of the things that we did in lesson number 1. Ladies and gentlemen, I just want to have a recap of the wave fronts. We know that if a sound is produced, let's take, we've got a person who is standing here, the person who is standing here, and there is a what? There is an ambulance. There is an ambulance which is also stationary. If this stationary ambulance produces a sound, then it means that the very same, if they are, closer to each other, of course, the very same frequency of sound that is being produced, it is what this listener is going to hear, because there is no relative motion. The two are not moving. You understand? So if we were to draw a representation of that, we can have waves like this. We can have waves like this that are equal. Some of the people, they represent it like that. But the best way to represent it is to show circles which represent waves which are equal in all directions. This side, this side, this side. Is because the sound wave, they are equal in terms of wavelength in all directions. But if this listener or the source, the ambulance moves towards the listener. If the ambulance moves towards the listener, it means that the frequency that this listener is going to hear, it will be increasing. That is something that we need to take note, that if a sound source, if a sound source approaches the listener, or vice versa. What do we mean by vice versa for this statement? We mean that the listener approaching the sound source. So that's what we mean. Then the what? The frequency of sound. The frequency of sound increases. What do we mean? If this sound source approaches the listener, the frequency that this listener is going to perceive or hear, it is going to be high. If this sound source produces a frequency of 520 Hz, this person who is being approached by this ambulance which is producing a sound of 520 hertz, this person is going to perceive a much more higher frequency. This person is going to perceive a much higher frequency because the sound source is approaching. But as this sound source is moving away, as the sound source is moving away, it means that this person is going to perceive a lower frequency. You understand? When the source moves closer to the listener, then the listener is going to perceive higher frequency. But as it moves away, the listener is going to perceive low frequency. So sometimes you may come across a situation. You may come across a situation where they tell you that this sound source produces 520. Then as it is moving, it produces 520. Obviously, this listener is not going to hear 520. But they tell you that there was a point as this car was approaching. There was a point where this person perceived 520. There was a point where the person perceived 520. So it means at the instant where this car was where the person is, it means the person is going to perceive the exact hertz that are produced by the source. You understand? So it means the person is not going to perceive 520, but immediately the car passes at this point where the person is, the person will perceive 520 and it starts decreasing. So that's how these things work. So at the instant the source passes the listener here and it moves, at that instant the person is going to perceive the equal amount of the frequency, the hertz. Okay, let us move forward. This was just, we know that when we have a representation like this means that the frequency of sound is equal in all direction. Then this one would mean that the source is moving to the left. You can see that what is happening here, the wave length are shorter, they are compressed, the waves are compressed, meaning that the sound source is moving in this direction as the frequency is going to increase in this direction. Then that's how we represent this diagram. It's just a recap from lesson number 1. Sometimes they say what is the physical quantity? The quantity that is related to pitch. The quantity that is related to pitch. The frequency is the one that is related to what? To pitch. So it means when the frequency increase, pitch is going to do what? To increase. Frequency decrease, pitch is going to decrease. So in this topic of Doppler's effect, the quantity that is related to pitch is the frequency. Okay, so now let us just talk about our formulae for Doppler's effect and how does it work. From lesson number 1, we have already introduced it. Now we just want to explain how it works. Frequency, this FL it represents frequency that the listener is going to hear. Then V plus or minus VL over V plus or minus Vs multiplied by Fs. Okay, so this Vs is the velocity of the source. This is the speed of that which produces the sound, the source. Then this is the velocity of the listener. This is the speed of that which hears the sound or perceives the sound. Remember, if they say that the listener is stationary, it means the velocity of a listener is 0. If they say the source is stationary, it means the velocity of a source is 0. We need to use some of our knowledge from mechanics about physics. Then what I need you to notice here is that this formula, we have Fs that is here. In general, this formula is like this. Do not be confused by the position of Fs. The formula is like this. Sometimes you can be confused when you are solving. This Fs is multiplying with the numerator, everything that is in the numerator. We can even say that the formula is like Fs plus or minus Fs over V plus Vs. That's what the formula is. This Fs must multiply with everything that is in the numerator. This is what you will need when you are solving questions. As you can see that we are trying to unpack the Doppler's effect formula. You can see that this formula have got a plus or minus, plus or minus. You can see plus or minus. This is plus or minus. So how do we deal with this situation of plus or minus? Because you know that in the calculator we don't have a plus or minus. The same applies to the when we are dealing with the quadratic formula where we have a plus or minus. Isn't it? We start by writing plus, then we go back and we remove the plus, we put the minus, then we get two answers. But with this scenario of Doppler's effect, we do not have two answers. It means it's either we're going to have a plus, it's either we're going to have a minus. When do we know what to do? This was me trying to expand the formula, but the main formula is this one. And you need to notice that this formula is going to change. This formula may change based on the scenario. When the source is approaching the listener, the formula is going to change. When the listener is approaching the source, the formula is going to change. But that 1 mark for a formula, when you start a question, don't try to change the formula. Use this formula as it is. Don't try to change the formula. You just copy this formula as it is. Okay, let us do these things. Look, yesterday I said, do not look at this formula holistically. Then don't look at it as a whole. Just look the listener part. The numerator is the listener part. The denominator is the source part. As you can see, we have Vs. This side we've got Vl. So this part is the part of the listener. This part is the part of the listener. Then this part is the part of the source. So we need to take note of that. Let us check. Here are one of the things that we need to use. Then, how do I set them? When the source is approaching the listener. When the source is approaching the listener, what's going to happen if the source is approaching the listener? Okay. It means that in the source part, this side, right? We will have a negative. We'll have a negative when a source is getting closer to the listener. When the source is getting closer to the listener, it means in the source it is negative. I can informally say, when the sound comes closer to you, what is going to happen to your ears? They are going to be irritated, isn't it? Your ears are going to feel pain. Then that is bad. It is negative. You understand? Notice that is not an explanation for what I'm trying to say. That is simple me trying to create a mnemonic device for you to understand that when the sound source come closer to you, your ears are going to be itchy, you are going to feel pain because the sound is too high, you're going to be irritated. So it is negative. You understand? It's a mnemonic for you to try to understand that, but that is not the explanation behind. When the sound source is approaching the listener, when the sound source is getting closer to the listener, when the sound source is getting closer to the listener, it means we're going to have a negative in this part of the sound source. Okay, then what does it mean when sound when sound source move away, when sound source move away, when sound source move away from listener? We're focusing on sound source for now. When the sound source move away from listener, we're going to have a positive, or we use a positive sign. When the sound source moves away, if they say a sound source is moving away, it means your formula is going to have a positive at the denominator. You're going to have a positive. When the sound source moves away, you understand? I've already told you that when the sound source moves closer, in the source we are going to have a what? A negative. When the sound source moves away, in the sound source we are going to have a what? A positive. In the sound source, I mean in the denominator where we substitute the information of the source. Okay, then let us talk about the listener. In the listener part, we have the opposite of this. So you don't have to just cram all the 4 points. Just cram one, and you know that if you cram the one, you know the others conversely. It's just the inverse of the other. The listener side, you just oppose this. You just oppose this. Meaning that since I've taught you this, you already know the answer. It means that when the listener approaches, when the listener approaches the source, when the listener approaches the source, we have a positive. When the listener approaches the source, we have a what? A positive. It means if a listener is approaching the source, we are going to use a what? A positive. Number two, when the listener moves away from the source. When the listener moves away from the source, it means we will have a negative. We'll have a negative. So it's just the opposite of the source. You understand? So it means in the source side, when the listener moves away from the source, it means it is the source which is moving away from the listener, isn't it? We're going to have the opposite. It means in the source side, since the source is moving away, we're going to have a what? A positive. But in the listener side, we're going to have a negative. So that's how we change this formula around. That's how we change this formula around. That information which I've just said, it is very important and we need to take note of it. Then let me show you how we get to change the formula. We get to change the formula, but I've already advised you that first step of writing the formula, don't change the formula using this information that I just taught you. Just copy this formula as it is. We are avoiding a situation whereby you are losing a mark because of making some mistakes. Copy the formula as it is. Okay, then let me tell you, if they say that the source, if they say the source is stationary, then I mean the listener. Okay, let me start by listening. If they say a listener is stationary, They say that a listener is stationary and the source is approaching the listener. The source is approaching a stationary listener. It means our formula is going to, we are going to have V, which is the speed of sound in a particular medium. They usually use 340, but because it's 340, the speed of sound in air, but sometimes it is going to change. So don't cram and use just 340. Sometimes it is going to change. You find that it is not 340. They've just given you what to use. So it means, since they're saying the listener is stationary, it means this VL is what is 0. Then the source was approaching a stationary listener. It means we're going to have 4. When the source approaches, it means we're going to have a what? A negative. Then it means this is the formula when the source is approaching the what? The stationary listener. Isn't it? The source is getting closer, and I told you that when the source is getting closer, it will irritate your ears, then it will be negative. That is a mnemonic device, the one of irritating ears. It's not the explanation behind, just to make you understand. Then we're going to have Fs. So this is the formula when the source is approaching a stationary listener. So this formula, you're going to change this formula, but it's the same formula, you just change. Here you just wrote 0 where there is a FL. But I advise you, do not change formulas just like this. Use this original formula, copy it, then you'll do the changing in the second step. You can write this formula as a second step for you to do the correct things. Okay. Then now, here is the advice. We mark substitution. We mark substitution only. We don't mark the maths. We don't mark the maths, the manipulation, changing these subscripts to make them subject of the formula. You make VS subject of the, we do not mark that. We mark substitution, meaning that when you copy this formula, you need to substitute each subscript, each value in the correct subscript. You substitute each value in the correct subscript, then we are going to give you full marks. Then the final, and we mark the final answer. For example, if they want you to calculate the speed of the source, it means, and they are giving you 650 as the frequency perceived by the listener. That's what you're going to write. You're going to substitute everything in the correct place. Then they give you 510. They give you 510 hertz as the frequency produced by the source. So you find that the question is 5 marks. You have substituted correctly. Right? Meaning that for correct substitution, here we're going to give you what? 4 marks. Then the final answer, it will contribute the 5th mark. We are marking correct substitution. Can you see? By simply substituting, you get full marks. Then remember, you need to use math to try and make this VS the subject of the formula. But we will not mark that long step of math. We only mark substitution and the final answer. So our learners, we advise you that please make substitution, make correct substitution. If you ever don't understand the math that you need to do to make this one subject of the formula and get the final answer, you will be safe, because you'll get 4 marks by simply substituting. You'll get 4 marks by simply substituting. Then that will be it. It is very easy. Ladies and gentlemen, it does not end there. Okay, if I were to ask a question in this scenario, was the source coming closer to the listener or moving away? Was the source coming closer to the listener or moving away? It means that the source was coming closer to the listener. Why? because the frequency of the source is greater than the frequency perceived by the listener. So this is the frequency that the source produced, but the listener heard a higher frequency, meaning that the sound source was coming closer to him. Or we are continuing with Doppler's effect. I was just explaining the formula for Doppler's effect, and I just told you that when the source is approaching the listener, in the denominator we are going to write a negative. When the listener is approaching the source in the numerator, we're going to write a positive. You understand, right? You understand? So let us move forward. Let us move forward. Ladies and gentlemen, I want us to take note of this formula. Sometimes the question will request us to calculate a frequency, and we will rush to use these formulas of Doppler's effect. You find that we were not even supposed to use Doppler's effect based on how the question is asked. From grade 10, when we were doing longitudinal waves, we learned that the frequency is equals to velocity over wavelength. Velocity over wavelength. When we talk about the wavelength, ladies and gentlemen, we are talking about the distance. Wavelength, this is the distance. This is the distance. We can even substitute that wavelength with distance travel. I can say frequency is equals to the speed over d for distance, for wavelength. So sometimes the question will request you to calculate the frequency. Just to find out, you need to use this formula if you are given the distance. So you need to take note of that, the wave length. Okay, so another formula is this one of dst. This distance is speed over change in time. Sometimes you are going to be given a situation whereby we have the speed over change in time. Where there is speed, I can even write v over change in time, because the speed, we are talking about the velocity. So distance is equals to velocity over change in time. For example, if you are given a graph like this, and the graph is like that. This is the graph. Then this is the time. This is the time. This is 10 seconds, for example. Then this is frequency. This is the frequency of listener. This is the frequency of listener, and you are given 620 Hz. You are given 620 Hz. So this graph reminds us of the graph of momentum. Graph of momentum. You remember that this line represents initial momentum, final momentum, and during collision. So it reminds us of that. But this is not a momentum, guys. It's Doppler's effect. This is a graph that is representing Doppler's effect. So what is the scenario here? It means that the listener was perceiving, hearing a sound of frequency of 620 Hz. Then suddenly there is a what? There is a sharp decrease of the frequency that the listener is hearing. Why is there a sudden decrease? We may even entertain this graph, because you will find that some other time this graph is set. Let us entertain it. What do we do? Why do we have a sudden decrease in the frequency? You can see that the frequency was 620, then it suddenly decreased. Why is there a sudden decrease? It's because the source is moving, the source is moving, the source is moving away. The source is moving away from the listener. The source is moving away from the listener. So since the source is moving away from the listener, what does it mean? It means that the frequency that the listener is going to hear, it is going to do what? To decrease. That's why we have a what? A decrease. You understand? Okay. What else can we say? What can we say about the wavelength and the frequency? What can we say about the wavelength of the frequency? It means wavelength is increasing. Is increasing. The wavelength is increasing. What about the frequency? The frequency perceived is in the wave is what? The wavelength is increasing. What is happening? The wavelength is increasing, right? When the wavelength increase, it means the distance between the two increase, right? Then the frequency is decreasing. The frequency is decreasing. The frequency is decreasing because the wavelength between the sound source and the listener, it is becoming larger, it is increasing. Then it means the frequency that is going to be perceived is going to decrease. That's why we have a sudden decrease. It's because the sound source is moving away from the listener. The sound source is moving away from the listener. So that is what is happening in the scenario of that graph. If ever you can be requested to explain, you need to be able to relate wavelength and frequency. When wavelength increase, then the frequency is going to decrease. That is the relationship. Okay. Then, while we are still talking about the frequency and wavelength, I remember yesterday when I was demonstrating to you, I gave you another demonstration. And that demonstration sometimes it can bring confusion. I said, let's say we have this and we have this. Let's say we have this too. When we talk about the wavelength, we're talking about the distance between these two, provided that these two are different waves. So if ever I can just give you a question and I say, which one is the wavelength? You may get a wrong answer for that. So I want to clear that. When we talk about wavelength, is the distance between two successive waves. Wavelength is the distance between two successive waves. So this definition, it is the one which can give us the correct answers when it comes to these things of wavelength. Let's say I'm giving you a wave. Here it is, a wave, a longitudinal wave. Draw it as if it's a transverse wave. Then I have this. It must end where it started. Then this is 2, 4, 6, 8, 10, 12. Then it is like that. I won't write units because these units they may differ. Or this is the distance. Let me write. This is the distance. That is the distance. Let me write it here. D. This is the what? That is the distance. The unit. These numbers are distance. Then the question might ask, what is the wavelength? What is the wavelength? A question may ask. Because of how I explained to you the wavelength, one may say that the wavelength of this wave is 2, which is incorrect. Because someone may say the wavelength is from this point to this point, which is incorrect. The wavelength is the distance between two successive waves. The distance between two successive waves, meaning that a wavelength, we're just measuring the wave of, the length of one wave. We measure the length of one wave, the whole length of one wave, the length of one wave. A wave must end where it started. One complete wave must end where it started. Meaning that if this wave is starting here, it must end here. So it means one complete wave is this one. This is one complete wave. So the wavelength for this wave is 4 meters. The wavelength of this wave is what? 4 meters. The wavelength is from this point to this point. That's why we have 4 and we have got what? 4. We've got 4. The difference is 4. So the wavelength of this wave is what? 4 units. We measure the whole wave from where it started until where it ends. Then another wave starts, then another wave starts. The question may come, how many waves do we have here? Here is the first wave. Here is the second wave. Here is the third wave. So we have what? 3 waves. We have 3 waves. We must not count these things, these crests, and call them waves. We have got 3 waves. If we were having something like this, what would we say? We will say that we have got what? 2 waves and a half. 2 waves and a half. Because that's how we get to judge the waves. I hope we are together. Okay. That's how we are supposed to explain the waves. That's how we are supposed to explain the wave. That's how we're supposed to explain. Okay. So now I want you to be conscious about something. When we are dealing with this formula, frequency is equals to velocity divided by distance or wavelength. Frequency is equals to velocity divided by wavelength. I've come across a situation, or you find that the learners they're trying to calculate velocity, right? I think that velocity here is going to be equals to what? It's going to be equals to frequency multiplied by wavelength. We just change this formula. This formula is provided in the formula sheet. You need to take note of it. And you need to check the marks if you don't understand. You find that say calculate frequency, 3 marks. It have got nothing to do with the frequency of that Doppler's effect equation, right? It have got something to do with this formula. And they will give you wavelength. You will be able to know that, oh, here they request me to calculate frequency in just a simple manner. They don't want you to calculate frequency trying to relate it with the frequency of the source or the listener. You understand? So I've come across a situation whereby they say calculate the frequency of sound. Calculate the frequency of sound, right? Calculate the what? The frequency of sound. Ladies and gentlemen, you know that a human being does not have a frequency. It is a sound that have got the what? A frequency, right? You find that they say a person is moving at 20 meters per second. A person cannot move this speed. The person is moving at 3 meters per second. The person is moving at 3 meters per second. 3 meters per second. That's a person, right? Then a person will just come and substitute that 3 meters per second here where there is velocity. And they said calculate the frequency of what? Of sound. In other words, they are saying a person is going to have a what? A frequency, which is wrong. It is the sound that is going to have a what? A frequency, meaning that for this velocity, Do not substitute the velocity of a person or of the object. Actually, let me write it. Do not substitute should velocity of object on this v. Please don't. The question will request you to calculate the frequency of sound in a particular medium. This v is the speed of sound. Let me repeat. This v is the speed of sound in a particular medium. This v represents the what? The speed of sound. If it is just in a medium, you know that for v it is going to be what? 340. But I told you that it is not all the time where it is going to be 340 they will provide to you, unless otherwise stated. Never substitute the speed of a what? The speed of a person, the speed of a car, the speed of anything, because you are trying to calculate the what? The frequency of sound. You are calculating the frequency of sound, meaning that here you need to substitute the what? The speed of sound. Because you are calculating the frequency of sound. It's like a human being. Does a human being have a wavelength? So what will you substitute here? Because some of you learners, you get to substitute the wave, the speed that you are provided of a source, of a car, of a what. No, you are calculating the frequency of sound, meaning that here you need to use the speed of sound. I'm just emphasizing that you need to use the speed of sound. Do not ever use the speed of an object, of a car, of a person who's running, of whatever. You need to substitute the speed of sound where there is v when you are calculating velocity. One last thing before we start treating questions. One last thing before we start treating question is this one, that be conscious of vertical projectile kind of questions. Be conscious. Some of the questions will request you. Okay. Be conscious of vertical projectile questions. In this topic of Doppler's effect, sometimes you will need to start by calculating the wavelength or the distance. Then to use this formula, for example, is equals to V over wavelength. For example, maybe you find that you are trying to use this formula, or we use that one of D is equals to V over change in time. These are one of the formulas of calculating velocity. This is it can become the velocity of the source, or obvious this one is the velocity of sound. You understand what is happening? So sometimes you need to be aware and you become conscious that some of the questions you cannot be able to calculate them without having a velocity. And to calculate the velocity, you can use these formulas. You find that these formulas are not working. Then you will need to use what? Vertical projectile kind of questions. What do I mean? You are going to use equations of motions. You will use equations of motion. You're going to use equations of motion kind of questions. You understand? Last year, trial exam, Doppler's effect, it was not possible for you to calculate that question for the Doppler's effect before using equations of motion, because you needed the speed of a listener. I mean, you needed the speed of a source. So you need to know that sometimes it will not be possible for you to solve that question using only the equation of the Doppler's effect. You need to use vertical projectile, then you come back and you use the equation for this Doppler's effect. For example, the question was that an alarm started to ring, and when the boy who was sleeping, it started to irritate him because it malfunctioned and he could not switch it off. Because it malfunctioned and he could not switch it off, he decided to drop it. He decided to drop it from the building, which have got the height of 15 meters. He dropped the what? He dropped the alarm from the building that is 15 meters high. So that alarm is the what? Is the source of sound. It irritated him until what? It dropped him. Meaning that when you use Doppler's effect formulas, you're going to come across that scenario. We are given the frequency that was produced by that alarm. We are given the frequency of that sound that was produced by the alarm. Isn't it? By the alarm, we may be talking about a watch that was making noise. Then it irritated him and it malfunctioned. Then he dropped it. Meaning that even if we are given the frequency of the source, what do we need? We need the what? The velocity of the source. So in order for us to calculate the velocity of the source, what do we need for us to calculate the velocity? I'm saying that for that scenario, you need the what? The velocity of the source. Remember, the source was just dropped from a 15 meter high building, meaning that you need to calculate the what? The velocity of that source using the equations of motion. Which formula do we have for calculating the velocity which have got a distance? We have got this one of delta y is equals to vi changing time plus 1 over 2 g changing time square. It's correct. Then it's correct. Then what do? We are told that the velocity, the height at which that sound source was dropped at, it is what? 15 meter. Then the initial velocity, we're bringing in the what? The equations of motion, vertical projectile. Initial velocity is what? Is 0. Meaning that here we're going to have 0 plus 1 over 2. Then we have got 9,8. Then we have change in time squared. Then what do? We start by calculating the what? The change in time. We'll be able to get the change in time. The change in time is going to be 15. 9,8 multiplied by 1,2 is equals to 4,9 change in time square. Then we divide by 4,9. Then change in time is equals to 15 divided by 4,9, which will give us 15 divided by 4,9. Did I do the right thing? Yes. Which will give us 5. It will give us 3,06 second. Right? Then we put the square root. Then our change in time will give us 1,75 second. Then that's what we have. It means this is the time it took for that sound source to hit the ground. Then remember, we're not interested in the time, we're interested in the what? In the velocity of the sound source. Then we need to do what? To calculate the velocity given the what? Given this what? Given this time, meaning that we need the final velocity. That final velocity is going to use the formula Vf is equals to Vi plus G change in time, right? Can use this formula. We know the initial velocity is 0. Then we calculate this final velocity. We substitute the time that we have here. Then we get Vf. So it means this Vf is the what? Is the speed of the source. Then we go back to our formula. Where there is a velocity of the source, we're going to substitute this. So I'm making you to be conscious that sometimes you will need to use vertical projectile kind of question. Sometimes you find that you're not using just vertical projectile. It is not vertical, it is horizontal, but you need to use the what? The equations of motion, because to calculate the velocity of a source, there are many equations that we can use to calculate the what? The velocity of a source. Ladies and gentlemen, we are reaching the end of this lesson. If you haven't subscribed, make sure that you press the subscribe button. Support this channel for it to grow. Lesson number 3 will be based on treating questions for Doppler's effect. Salute.